Okay, welcome everybody to today's installment of our California Dreams Technical Seminar Series. We are excited to have HRL here with us today. We're not only excited to have HRL as our seminar series presenter today, but we're very excited to have HRL as one of our important partners in the California Dreams Hub and one of our 3 DoD volume foundries. And we are particularly excited by our set of speakers today. You see Jung's name here. I'm going to risk stealing a little thunder just by saying Jung is going to have help from colleagues today, including Andy Fu, Dave Chow, and Kevin Geary. So we are grateful to have that group here with us today. And with that, I will hand it over to Jung, who's going to talk about work in GaN technologies that I know evolved from, has come out of some of their DARPA work as well as others, I'm sure.
Right. Thank you, Steve. Thank you for invitations actually to this very nice webinar in the California Dream Hubs. Actually, we are honored to be here, and then we are very honored to be happy to be part of this California Dream Hub. It's a very exciting hub with the all the hub members with a very high tech, high-end technologies. So it's very good team members compared to other hubs. Actually, to be honest, that's my 2 cents. And so we're going to talk about the HRL's GaN technologies today. When this HRL, I think some of you may know you, but know us. This HRL invest in the GaN dating back to 1997. So it's been a long time, HRL invest in this GaN technology to become a real technology in the future. And so we are heavily developing this one through the governments or even in our own internal R&Ds and some of the support from our owners, right? So I like to spend some time to actually, if you don't mind here, to thank so many people actually contributed to this HRL's millimeter wave GaN or generally RF GaN technologies over the time, right? So, and I think I especially like to thank some of the external collaborators also, Professor Patrick Fay and all of them. And then, of course, I think Professor Umesh, we always learn something from the UCSB. So, and Peter Ashbeck and Professor Dmitry Pavlidis. And of course, this work, I think a lot of work is done by also our, ex-HRL colleagues. I think KSK is sort of the deep person here with Miro and Dave, Sean, Yukao, Longming, and we have so many of them to name. So with that, I think I want to go over to next slide, which is my agenda today. So I think the first we're going to go over the HRL's RF millimeter wave GaN overview, and then we're going to dive into technical stuff a little bit. Say, so what's the challenges in the millimeter wave systems, and then what are the opportunities? How you address that, right? So what we have done within HRL for a long time, we evolved the GaN, or developed the GaN, always with cutting edge performance, and always we come up with the next gen millimeter wave GaN device to address those challenges in the systems, right? So we'll go over that, and I think I like to end that this majority of my presentation is actually be part of the T3R, so the very high speed, but at the same time, can we get the linearity and the efficiency at the same time in the millimeter wave, right? So that has been always challenging the GaN technology compared with in the FastPipe HBTs. So can we address the linearity part of the GaN, right? So that was actually done on the DARPA DREAM program. So I want to share sizable amount of the content here to show that, right? There is a feasibility to that, okay? And we'll do the Q&A, okay? With that, Dave?
Okay, thanks. So actually, I want to repeat what Jeong said. Just in one thing, I want to thank you for inviting us to do the seminar. I've really been getting a lot out of these seminars. I heard Bobby's last week, and actually, I was super impressed that Bobby, who's the president of his organization, could give us such a thorough presentation on the technologies offered by Teledyne. Thankfully, I don't have to do that. Jeong is going to take care of most of that for us. But I guess I would say HRL, just a very quick overview. We are the former Hughes Research Labs, but we haven't actually been Hughes now for a long time. 1997 was the last time we were Hughes, and still some people out there call us Hughes, and that's okay. But our actual name is HRL, which 3 letters, it's not an acronym, HRL Laboratories. We are jointly owned by 2 large companies, General Motors and Boeing. But actually, a large fraction of the work we do, I'm going to say over 80%, the actual number is higher than that, is work we do for the US government, primarily research and development contracts that we have to go out and win competitively. And it's really great to be teamed on this hub with some organizations that I would say we often do compete with for programs from DARPA and places like that, but for whom we also have tremendous respect. I mean, these are some really good companies that do amazing work, and for us all to be together in the same hub is really an amazing opportunity. So we're really enjoying that and looking forward to the collaborations. We are a little bigger than we used to be. Today we are 1,100 employees. I'm going to say in very round numbers, we're more than a $500 million company today. And we have 5 sites. We used to all be in our one campus in Malibu, which is still our main campus. But today we have 4 other sites. The one in Camarillo is primarily focused on large format infrared focal plane array products. The one in Westlake today is mostly administrative, but it will house labs there. We'll have a lot of our mixed signal design work and also some cryogenic test operations there. And then in Calabasas, there are 2 stars, one of which is a rented property primarily for storage, but the other of which has labs that do information science and also RF measurements and a radar facility and some optical test labs and a cryogenic test lab. So really quite a bit more footprint than we had when we were all on one campus in Malibu. Okay, and one more slide, which I'm not going to talk a lot about, but of course, this maybe it's partially our fault that people still call us Hughes, because we put up slides like this where 75% of it was done, or like at least half of it was done while we were still Hughes, including the world's first laser in 1960. But it has been an amazing place to work. I've been at the place since 1990, so that's 35 years. And although the place is very different, there've just been a tremendous number of first technology demonstrations done at HRL over that time. All right, I'm going to turn it over to Kevin. Is that right?
Yes. Dave, I think I just wanted to mention that we started RF GaN Foundry 2021, right? That's right.
Yeah, I guess I assumed that Andy was going to tell us about that.
Yeah, that's right.
Okay.
Yeah, so that is our part of heritage. So happy to be happy to include that. Okay, Kevin.
Thanks, John. Hi, folks. Kevin Geary, director in our Sensors Electronics Laboratory. Much of the technology you'll hear about today is covered within this part of the organization, along with our Microfabrication Technology Laboratory. Want to thank the hosts here today, and I see a lot of familiar faces in the community joining us today. So thank you. It's a pleasure to see you on board here. This is a one-slide snapshot of the technologies and areas of interest of our part of HRL. We're really targeting RF and millimeter wave subsystems, developing solutions for both our owners and our strategic customers. In that upper right corner, you see some images of various phased array, large format millimeter wave and sub-millimeter wave phased array solutions that we've developed over the years. These are building blocks that would plug into, say, a radar solution, a snapshot or an example, which is off to the upper left corner there. In some cases, we're developing these parts and components and integrated subsystems from scratch. In other cases, we're leveraging the COTS hardware solutions in the community and putting them together in a smart way to solve a customer problem. We have a number of efforts integrating antennas and apertures into various platforms. That those solutions can take on various forms depending on the customer and the need. Some of these take the form of conformal solutions. Some of them are hidden or transparent. In some cases, optically transparent, if that need is there. But a large antenna aperture competency within the laboratory. A lot of the subsystem solutions that we build and develop, they build on a lot of advanced packaging and heterogeneous integration, 2.5D, 3D solutions. We're developing some advanced capabilities under a number of DARPA programs, and we're a partner with the TI, Texas Institute for Electronics, and the Next Generation Microelectronics Manufacturing initiative through DARPA. So a few graphics there of the types of packaging solutions we've been developing over the years are in that lower left corner. And then the bottom right, you see some cross section of a T-gate, advanced GaN transistor. The most of the talk will dive into that, so I won't go into that in detail. But the point being, we're focused on the end systems and needs of our customers. We develop component solutions to meet those needs if there's an innovation that's required at the component or device or materials level to reach that groundbreaking benefit for our customers and our owners. And we'll do that within the electronics domain, within a computational device domain, among others. So I'll turn it back over to you, Jeong, but it's a wide array of technologies we're looking at HRL. If anyone has questions offline, I'm happy to field those in subsequent communications.
Thanks, Kevin. That's great. So this is slide 6, right? So people are jumping over to Andy Fu to talk about the MPW Foundry. I want to describe a little bit about the HRL's GaN history. So I know the Umesh at the UCSB made so much breakthrough and then jumpstart. We learned a lot from the UCSB. Over the time, we witnessed so many technical breakthroughs. Actually, I'm actually part of the, I joined the HRL 2000, so I witnessed so much, the technology breakthrough from early on. So I was very happy to be part of that. And so I want to spend a little bit of time here, right? So you can see the overall view of the HRL technology development. So look at that early, even before the 2000, right? HRL fabricate GaN ham to the T-gate. Gate length was 250 nanometers. FT was like 28, so and Fmax is 40. It's pretty low speed at the current standard, but that back then that was very good. And then quickly, I think this is a early part of Miro's work, and able to scale the gate length down to 50 gigahertz, actually around 2000. So very pioneering work, right, at the time. And we're able to push the FTF max 110 and 140, right? And then if you look at here, this is device development, and this is mostly amplifier side here. And so you're able to get to T2, so-called technology within HRL, our nomenclature. So T2 is gate length about 150. And then I think the major thing happens on the DARPA Next program, which basically KSK developed out the T3 and then T4 and T4A, right? So able to scale the gate length 40 with very high speed, and then also scale gate length down to 20 nanometers in the GaN. So that's the state of the art, and they push the FTF max almost half terahertz, right? That's actually great work. That happens around 2010 and 2013, okay? And then later that, one of my contribution is actually, okay, so we learned a lot from the T3. Can you make a T3 more linear, right? So we call the T3R, the T3 speed with the linearity, right? So this is actually developed on DARPA DREAM programs. So stay on the gate lengths, roughly 50, 40 nanometers. And quickly we realized that, oh, okay, we can get the even high PAE, high power density than the T3. And then speed is actually very comparable to the T3. So, and Fmax is close to 360 gigahertz, right? And using that, we were able to develop a lot of the amplifier demos and circuit demos. And so if you look at here, the latest work is that we had actually, this is done on the DARPA DREAM programs. We are able to make a Ka band LNA low noise amplifiers with very high linearity figure of merit, right? So OIP3 stand for the linearity per given power, right? So the ratio is a figure of merit. Typically runs on a 1 or 2, but we are able to go beyond, well beyond 10, actually up all the way to 50, right? So, and then go to 94 gigahertz, very high efficiency operations. And also we made a W band PAs around 2023. And exciting development is actually, can this T3 can be used on transmitter side under linear conditions, right? So we've been testing a lot of testing this transistor technology on the 64 QAM or 256 QAM. So I will show you that, some of the data at the end, okay? So this is HRL's technology portfolios. So we have a T3, and then scale the T3 in some source train spacing. So the reduced parasitics, that's a T3.5. And then we are jumping into T3R, which is, as I said, maintaining the T3 speed with the linearity at the same time, right? So with that, this is sort of our current focus. But Andy, okay, so before I jump into Andy's slide, and so we are very excited about to be part of the California Dream Hubs, and we HRL currently executing the 2 projects. And then one of them is actually GaN AMP project, and we are part of the Northrop Grumman team. And then the other one is the 5 and 60 topic number 1, right? So if you look at here, our core technology is a 40 nanometer T3R. And this technology also, this project also utilizes 40 nanometer T3R. So, and we're trying to demonstrate a higher MRR at the end of the program from 4 to 6 and both sides, and then demonstrating some of the B band and W band PA with sizable power and efficiency, right? Okay, so that's our current California Dream Hub project. We are very happy to be part of it. Okay, and Andy?
Hi, John. Can you hear me?
Yes.
Hey. Hi, everyone. Yeah, thanks for attending. So on this slide, I'm going to talk about our HRL's MPW GaN foundry. So we're the first sub 100 nanometer GaN on silicon carbide foundry that offer a multi-project wafer. And so starting in 2019, we initially performed some early access PW runs using our T3 GaN, 40 nanometer GaN. And then with support from a couple of government programs, the MGM and Starry Night, we successfully deliver MPW runs on a quarterly basis, and that's since 2021. And we've maintained that for the last 4+ years, and with a very good on-time delivery track record. And so this is an effort, an effort that we started last year. We are in transition phase from our T3 to the T3L high linearity technology node. And the impetus for that is for improved performance and reliability. And so what you see on the right is our T3L T-gate with a mini field plate structure that's built on our graded channel at B. Our technical team actually is working very aggressively right now to support product qualification, and this is and we're working with several key customers on their efforts to insert the technology into the systems. And this effort is also supported by the StarNet program. And our GaN foundry is an open foundry that we work with a mix of commercial, aerospace, defense, as well as research institutions. And we also engage with not just domestic customers, but we will also work with international customers who are interested in the kind of this, particularly on the high frequency ranges of their application. And as part of our foundry service, we provide our PDK in two versions, one in ADS and one in AWR. And we also provide free training for designers to evaluate our technology. And for customers that want to onboard onto our MPW, we provide good support for design submission, as well as getting their design verified, achieving DRC clean status. And I should mention that our GaN foundry is also a certified trusted foundry by DoD DMEA. And we actually recently went through a renewal certification with them. So for those of you who are interested in evaluating our technology or kind of working with us as a potential foundry and participating with MPW, we encourage you to kind of engage with us first and foremost through the Hub and Moses 2.0 storefront. And otherwise, you can also contact me directly at the information there. Thanks. Back to you, John.
All right, thank you, Andy. That's great. So yeah, please contact Andy for any questions and informations. Okay. So, all right. So I think I'm going to dive into more technical stuff. So and then hopefully we can finish up a little early. So we actually also open up the floor for the Q&As. Okay. So the let's see, in the commercial world, right? I'm going to touch on the like opportunities in millimeter wave in the commercial world and the defense world. In the commercial world, we all know that the wireless connectivity, right, transformed every 10 years, right? So 5G actually launched the 2019. So according to this is actually from Nokia, 6G is supposed to launch close to 2030 timeframe. I guess TBD, but that's actually a current plan. And there is a lot of band, right, in the 5G and 6G band. Currently, FR1 is deployed and we're using it. Then FR2 and FR3 is going back to 7 to 15 gigahertz band, and then FR4 and 5 on the further out, and that is basically I think this slide from the actually I think entity. So trying to cover large areas with extreme data rate with the lower latency. So that's sort of the snapshot of what the commercial world is doing it. So I want to touch on the challenge side of that, right? So I think Peter knows this area so well. So in my perspective is millimeter wave give you bandwidth, but to maintain the spectral efficiency, people typically requires higher modulation schemes, either QAM or different modulation schemes. And there is called EBM, error vector magnitude metric, to deliver communication with the lower bit error rate, right? So I just want to tell you that this is 5% EBM constellation start distorting the constellation when the EBM comes higher. And then also this 1024 QAM, right? So, and 1024 QAM delivers a lot more the spectral efficiency, but I think it requires a lot more stringent EBM specs, like 1%-ish, right? And a lot of the FR1 systems use the DPD to linearize RF chains. When you go to higher frequency band or higher bandwidth, DPD starts getting more challenges. And then instead of linearizing one transmitter chain, you have to linearize array of the element. So that's another challenge. So that's very strong, very active ongoing effort, and linearizing the front end. And DoD side of that is that, and of course, there is EW systems. If you want to do both jamming and communication at the same time and a single aperture, you need the linearity in the systems. This is well known in the Navy systems. And then SATCOM is, of course, right? The power is limited in space. So if you want to open up the dynamic range of the SATCOM systems, you need basically current rule of current practice that requires more powers. So can you get that, higher dynamic range with the lower power? That's always the challenge and trade-off. And if you want to move the 5G systems into non-terrestrial platforms like space or in the LEO constellations, you're going to count the same issue, linearity and efficiency challenges, right? So can you get there with the higher linearity and high efficiency at the same time? And both the receive side and transmit side. That's sort of the question actually we are trying to address in DARPA DREAM programs. So here is sort of the snapshot of the current state of the art, right? So if I have the linearity figure merit in the y-axis, and then this is the receive side, and then I want a very high sensitive receivers, and then most of technology runs in somewhere. We can deliver the sensitivity here, but the linearity figure merit always lacking. And so can you get the high dynamic range? So in DARPA DREAM program, trying to push this linearity figure merit all the way to like 20 dB. And I think in device level, we met that. And then amplifier level, we have to get to about the 17 dB, okay? So that's sort of one of the highlight of the DARPA DREAM programs. To do so, we had to modify the GaN technology to deliver these specs. That's why we came up with the T3R, okay? And transmit side, the same thing. So transmit side, and I want to have higher linear transmissions with the lower power. So that's always a challenge. If you look at most of the amplifiers, right, and just follow this figure method like 0 dB. So can you get up to the very higher, this linear figure method in the transmit side? And that's also been a challenge. So I want to show you some of the examples, what the T3L do under the transmit side. And so, okay. And I think I copied some of these figures from the actually book. And I think this chapter written by Peter. And so tell us what's the advantage of GaN over the other semiconductor technologies. Of course, higher breakdown, lower loss in the good contact, so the lower parasitics, and higher saturation velocities, right? So it's all beautiful in the low frequencies. So what happens is that when you go to higher frequency, so many problems start showing up, okay? So that's a challenge in pushing the GaN to the higher frequency devices. So historically, this is low frequency system is well developed. This is earlier work by Yipeng from UCSB, right? Able to demonstrate 30 watts per millimeters, right? So huge record power density coming out of single transistors. And then going into millimeter wave, this filter plate has to be integrated. So this integrated filter plate. So, and then this is done, and HRL and also UCSB. Actually, this is Thomas's work when he was at UCSB. And we were able to scale this filter plate to 90 nanometer filter plate, push the FTF max, 100 and 210 gigahertz, but still not quite sufficient. So most of the high frequency technology is done by T-gate. So without the filter plate, parasitic is reduced, the speed goes up, but you lose something, right? You gain something, you lose something. So so that's, I want to show you some of the challenges we had and then our community had, okay? Of course, this is, of course, gallium polars, but there's UCSB's nice work is from the N polars, okay? So the good thing is that GaN, right, does scale up in terms of speed. So if I follow gate length is reduced, FT goes up. And then average velocity is about roughly 1 is 7. So, and maintains relatively good. So FT, Fmax can be close half terahertz, right? This is only case work, okay? And to do so, because of that, I can maintain the reasonable breakdown. So Johnson figure merit is also very good. So this actually done on the DARPA Next programs. So if you design the sort of the amplifiers, right? This is amplifier efficiency versus P set. This is from the Professor Wang's, and see that the GaN is always outperforming any other technologies in terms of the output power and efficiency, right? So GaN is sort of the pretty good technologies. We all know that, and the challenge is this, right? This is long channel GaN, and then you start going to gate length 140 nanometer T gate. So this is actually static IB. And under the RF drive, the actual IB shows that it's not like static IB, right? So this is what we call current collapse, right? So device actually output conductance goes up, and then the knee voltage shifted out, and so that impacting the efficiency. At the same time, maximum current drops, so the impacting the output power density. And that's getting severe when you go to 40 nanometers, right? This is earlier Miro's work. I published in 2017. So you see that dramatic difference between static versus the dynamic performance. So that needs to be fixed, right? And the reason is that there's always a virtual gate formations, right? Near the gate drain side where the electric field is high. So basically you deplete the channels and basically everything happens. This actually, Umesh actually published this earlier work in 2002, right? So that tells that we need to solve this one. Standard technique to solve this a field plate, but field plate comes with a speed trade-off. So that's a challenge in the high-speed devices. So if I overlay, sum up the challenge in the millimeter wave GaN transistors, this is power density versus speed of transistors. So, and most of the low speed transistors down with the field plate able to deliver very high power density and efficiency because device acts close to ideal situations. And when you go to very high speed transistors with T-gate, power density drops. So due to the current collapse, right? And so the second challenge has been the linearities. The GaN, earlier GaN, known to be very soft. So what that means that the AM to AM is high, and the AM to PM is not controlled. So if you actually analyze the linearity, non-linearity of the GaN, these conventional GaNs, this is actually done by the Professor Patrick Fay, and it's the same thing as like CMOS. Most of the GM non-linearity dominate, first and second derivative dominate. Also CGS and CGD comes in, and or combination of them. So we basically have to do linearized GMs. Also have to control the capacitance. Okay, reactive element of the GaN transistors. That's not easy actually. So to solve that problems, so here's my wish list was, right? So back in during the DARPA DREAM programs. So what the next generation GaN device means, right? So we want to have very high speed operations. Usually high speed operation translate into lower noise. That's usually easy to get. And But can you maintain the linearity at the same time? That's hard to get, okay? And then when you go to higher transistor, high-speed transistor, current collapse comes in. So if you mitigate that, you can maintain efficiency and the power densities, okay? And most challenging one is, can you maintain large signal transmitter linearity, right? CO by M3. So that's what I mean by the next gen millimeter wave GaN transistors, right? So there are a bunch of approaches out there in the community trying to address that. So this is actually Professor Rajan's group and OSU. And so this is basically bulk graded GaN channels, right? So he was looking into that. And then I think this is MIT Thomas's work, and make the GaN into the thin structures, just following what the CMOS does. And also this is a UC San Diego's work, Professor Choi's work, and trying to make the also a thin hemmed in the GaN. And there are many other approaches, scandium aluminum nitride. This is the Teledyne case work and the bridge FET. And this actually Northrop Grumman East, the slack FET. And HRL's approach was a graded channels. And what I mean by that is there is a graded epi in between the barrier and the channels, okay, to linearize the GaN operations. And of course, I think Ampola work from the UCSB. So it's good that the community trying to address the key challenges, both the linearity and efficiency challenges at the same time. So that's very nice. And I want to talk about that the HRL's work, which is graded channels. So traditionally, we've been working on the GaN for a long time with very simple heterostructures, the barrier and the GaN. And then we do see sometimes like softness of the AM to AM. And so we introduced the graded channels in between the barriers. And that brings out some innovations, okay? And then also introduced the mini field plate gate, T-gate here, trying to maintain speed and then possibly electric field management. And then third is the manufacturability of the T-gate structures, okay? So, so here is something actually we learned that during the course of this graded channel GaN development, right? So the T3R. So a lot of things actually came from the Professor Patrick Fay. And so why the GaN is nonlinear, there's intrinsic physics behind it. So the saturation velocity is also depending on function of the carrier density, okay? So if the carrier density is too high, there's electron phonon coupling that slow down the actually velocity, okay? So, and also this DJ is at Cornell was part of this contributions. And so if you spread this peak density over a little bit, if you spread too much, you're going to lose transconductances. So just optimize sweet spot and spread a little bit, and then just bring the density down, okay? So when you do that, the GM is, this is actually Patrick's simulations. So this is without graded channels, this with graded channels, okay? And then speed went up. This is the standard one, and this graded channels. And most important thing is that actually peak electric field is reduced. So this is simulations, and this is conventional argon GaN hemmed. If you introduce it, and peak electric field is reduced even without field plate. So allow us to push the breakdown voltages higher and push the power density up. Okay, so there are a lot of innovations happens over the time by simple change in the epi stack, right? So that was actually our discovery. And I want to show you some of the actual data to back it up, our innovations. So the first thing is the speed actually able to maintain. So this is actually 50 nanometer gate lengths, right? 50 nanometer gate lengths. able to maintain speed FTF max close to 40 nanometer Elgin GaN HEMT. Okay, so that's one. And in speed is high, device level logic figure is very, very low. So this is to our surprise also to us. And this is actually measured noise figure at device levels. And some of them is actually the 2 data point here. And typically 30 gig, you get half dB, the best one. Typically we run at 0.8, and you can go all the way to W band. So this sample was measured at the UCS Air Force, published these numbers. And then the linearity figure merit is actually plotted here. So what I'm plotting is a power consumption goes in the device levels, and then OIP3 is the linearity. And most of technologies, this figure is below 10, we're able to go to 20 dB. Okay, this is 30 gigahertz. Okay, so there are two breakthrough happens in the receiver side. So we went on and fabricate amplifiers, and so we were able to get a very good low noise amplifier and Ka band about 1 dB. Okay, so that's good as you can get too. And then this one is the linearity figure merit. And so this is actually saying linear figure merit is about 17 dB, around 30 gigahertz. Okay, and just to contrast, right? If you take the by the conventional GaN or L-GaN, gallium arsenide, the linear figure merit is typically below 2, right? This is actually 50. Right? So that's huge improvement in linear figure merit. That translates into power saving in your large arrays, right? And so I want to talk about the transmit side. So I spent probably like another 5 minutes to cover transmit side. So I just want to tell you that this is the data typically we getting in the conventional structures. And when you go to very high device speed, right? So power density tended to be lower. And T3R on the DARPA DREAM program, we're able to push this one up to 6 watts per millimeter at 30 gigahertz. Okay, so that's actually first achievement. And it turns out reasonably stable. Okay, we did not work on heavily on the reliability or stability of these transistor technologies back then, but it's already started showing that transistor can be very stable. So what it does is that this RF stress test at the peak PAE. So 62% peak PAE, 30 gig, we bias over 250 hours, and we lost about 0.3 dB. So this large signal RF stress test, they survived. Okay, and push that into W band, and so typically runs about a linear gain of about 3 dB at 94. And then this is efficiency, 45%. Drain efficiency actually 66%. So that translates into the device. If you improve the gain, then I think is the your PA can go even higher, right? So this is actually drain efficiency 66%. That's an amazing number. And of course, I think is the M-Polar from UCSB gives very good performance in W band, right? And in our case, a higher efficiency at a little bit lower power density. Okay, so that's where we're operating. And we went on actually fabricate W band MMIC. These are the transmit side MMICs. This is actually 2-watt design. This is even higher power. And initial was success. This is actually a measured S parameters actually about 22 dB. So 7.33 dB per stage. This 3-stage design and these simulations. So it's closely matched, not perfectly matched, very closely matched. So that was under the control. Okay. And I want to talk about a little bit of two-tone linearities, which is actually very important part of the actually amplifiers actually in the systems. So what this one tells us, I'm plotting, testing the device on the two-tone, looking at the PAE reaching the 62%, and then I'm trying to back it off, and where the IMD3 is a 30 dBc right here. At that point, PA is very high, above 50%. Right, so that tells me that I think this one has a chance to get into transmit side under the communications. Okay, and so this is my last slide. So we test this device on the 64 QAM. Okay, so this one is output powers. This gain is started going down like this on the RF drive, and this efficiency coming up, and the EBM is in the red. Okay, so the lower the EBM is always better. In the 64 QAM, if I put the 5% threshold, so if I put the 5% threshold, and then associated PAE is above 40%. So this is actually very good number. So, and we'll continue to working on this one to optimize in the T3R under the communications. Okay. With that, I really like to thanks California Dream Hubs, and of course this work is not possible without the support from DARPAs. So the Tom, YK, and Dan, only when Dan was at the MTO, and his teams. Of course, John Albrecht, Philip, Mark, John Jorper, all supported GaN programs, and sizable effort came from actually ONR over the time, from of course Paul Mackey and Dr. Harry Dietrich, and of course Boeing support. Okay, with that, I think I'd like to close.
Thank you very much, Sejong and team. Do we have questions?
So I have one perhaps for Jeong. It's really amazing that you get so many benefits from the graded channel invention and development. Not just linearity, but the speed and also the breakdown. So do you know how the breakdown that you're getting compares with sort of theoretical expectations? Like, do you think in the future you can get even higher breakdown with those dimensions?
I think if I asked this same question to Patrick Fay. So Patrick did a lot of, Patrick Fay at Notre Dame, right? He did a lot of simulations for us.
Sure.
And his answer is yes. Actually, he published a paper, and Johnson figure of merit is higher now with graded channels. So I did not include that, but if I follow the Patrick's oops, where is it? 1 second. Okay, so Peter, right? So this is what we learned on the top of next programs, right? Johnson figure of merit is the 5 terahertz and volt, and Patrick's number is actually 7. So T3R can push out the breakdown without losing the speed much, so able to get up to here. And experimentally, we see some indication of that. So when we test linear power scaling, so yeah, oh, sorry, I did not include here. But when we test this linear power scaling, right? And so at 22 volt, we're able to push this 6 volt, 6 watts per millimeter operates at 22 volt BDS. And the gate to drain spacing is only like 0.6. So it's higher breakdown, gate to drain breakdown. And compared to without the graded channels. And there's a physics behind, and according to Patrick's simulations, I mean, this is actually the magic, right? Actually, to be honest, the magic to me was, can you maintain the peak electric field without the field plate, right? So field plate always add parasitics and slow down this device. And so Patrick think there's a physics spreading of the 2D charge to the quasi 2.5 D-ish, and peak electric field is lower. And so that's the magic. And we trying to validate experimentally. That's tough. Yeah, that's tough. But
Who else has a question? Or is there follow-up from Peter?
I can follow up. I have a follow-up if no one else does. This is Roger Lake at UCR. Hi.
Hi, Roger, please.
Hi. So this magic here, is it, you mentioned that it has to do with optical phonon scattering, and it's more effective at high energies, I guess. Was that what you were stating there in the box?
yeah, so the GaN, right? Hey, Roger. So
Hi.
yeah, it's not like you know, what I mean by the magic is that this is something we unexpected. So and we expected actually this one, right? And we did not expect this number. I think the way it works is that the optical phonon energy in the GaN is about 92 millielectron volt, right? And the velocity under the channel, right, is actually a function of the carrier density. The reason is actually optical phonon coupling, right? So so if you reduce,
I guess in the back of my mind, I was thinking at at the voltages you work at, 92 millivolts is almost negligible, right? You've got a lot of high energy electrons flying around. Once you apply a voltage, source drain voltage, it's just surprising that changing, that this really, this is sort of like an equilibrium distribution, what you're showing, but after you apply whatever source drain voltage you're applying, you probably have all kinds of very high energy electrons flying around.
that's probably true. That's probably true.
Sort of like, the kind of simulations Max Fischetti did back in the early 90s. Like once you apply a certain voltage, the mobility almost doesn't matter because the optical phonon scattering takes over. And everything comes out roughly the same.
Roger, I think it's the I'm not the expert. I think so. This is actually when we present this concept right early on in the conference, and there's a lot of discussion actually. And then DJ at the Cornell and the Patrick at the Notre Dame and some other folks, and so it is actually happening in the experimental side. Actually, we actually okay. The problem with the GaN, with very high scale GaNs, if GM is too picky, okay. If the GM is too picky, the designers doesn't like, okay. And so we want to make the GM to be more nice and smooth. So that happens, right? So that was good. And then we actually look at this charge modulation under the gate with the CB, capacitance measurement. It does show that, slowed those linearization. And we do not see this one, but experimentally we do see it. So we're able to get, even the gate length is like a larger, right? 20% larger, but the same speed, right? So that's one. And this one was very tricky to validate it, but only way to validate was, right, power density. So able to push the power density up to 6 watts per millimeter. And I published the paper, and then is a compare with the conventional ones. Conventional ones actually how to push power density up, but by grading it, we're able to push the power density up. So
it couldn't just be like interfacial scattering. When I look at your two charge profiles, you know, one is the charge is really pushed up against the interface, the other is kind of more spread out away from the interface.
Yes, right. That's right. Somehow that plays role somewhere.
I see. Okay.
Yes, yes. No,
very, very interesting.
no,
sure
I think yeah, I think this is actually one of the big problems we want to solve in the GaN, right? You know, and as frequency goes up, right? And the GaN is well known to be used in the radar because in a very high power, you know, per element. You know, we like to have the GaN to be in the millimeter wave COM, right? And you got to have address AM to AM, AM to PM, which Peter knows very well. So
we have one more.
No.
Sorry, go ahead, Richard.
Thank you.
I didn't mean to cut you off. We have one more question in the chat as we're getting close to the top of the hour. John Lee, do you want to come off mute or do you want me to read your question?
Hi everyone, Chen Li here. I'm just curious, like with all these data showing here, I mean, very interesting. And was there also work put into look into the capacitance behavior, like particularly the gate to drain capacitance?
Yes, yes, we looked at that. So we looked at CGS and CGD, right? So actually, I did not show you here, but the we do have actually PDK. We have Angel-Lock model, and then if you plot the AM to PM, you know, okay. So I just want to quickly, right? To get AM to PM, and we don't have to back it off 6 dB. We can only need to back off 3 dB, still get the meet the AM to PM EBM metrics, right? Because AM to PM is reduced. The reason why AM to PM is reduced is the capacitance is linearized. So that's something actually I did not mention, right? That's very important. Capacitance also linearized. So
cool.
Yeah.
Okay.
So that's actually a huge benefit, actually, to be honest. Yeah.
Right. Yeah. I mean, that sounds very interesting. I guess, yeah, would be very curious to like take a closer look at the PDK and to understand it more. Yeah.
Yeah. So we have a test bench in the AWR, and then actually simulate the whole chain, communication chains, and then you can see the AM to PM. So question,
cool.
I just caution you, right? We did not validate this AM to PM in the measurement. So that's something that next we want to do it. But
Got it.
Yeah, but yeah, got it. Yeah.
All right. Well, thank you.
Yeah, thank you.
Amy, do you have a parting slide to bring up while we finish up here? Hopefully something is coming from Amy, but while that's happening, I will thank Jung and the team from HRL, Dave, Kevin, Andy, and I see lots of others from HRL have been in on the summer seminar. We really appreciate your participation. There's a QR code here that Amy has up for link to register for the seminar series so you get notifications for future seminars. And then the last slide, I see Amy's looking to switch, but you can see the last slide here. We have some really great seminars coming up that will try to live up to Jung's fine job here. We have Gabriel Rabiz, many of our friends speaking next week, and Umesh, who has been referenced in today's seminar, as is often the case the week after that. Azita Amami, we're very lucky to have from Caltech presenting the following week. And then we have a slot the week of GOMAC Tech that we're working on filling before, and we do have a candidate there that we're not ready to announce yet. And then Mark Rodwell will finish out March for us. So we're looking forward to all of this, and I think we can wrap up unless anybody from HRL has anything further to say on the way out.
No, we'd like to thank you, Steve, for
Yeah.
arranging this webinar.
Okay, well, thank you everybody for attending, and thanks again to HRL. We'll see you next week.
Thank you.
Bye, everybody.